Okay, I think we can probably get started. People will join in if they come in later. So thanks everyone for coming to another one of our virtual public lectures. If this is the first time you've been joining us, you can ask questions in the chat, or if you're watching on Facebook, you can ask questions on the Facebook post in the comment section, and we will read them. And then I will pass them along to Marcus. I think that might be it. So without further ado, Marcus Merryfield is a graduate student at the McGill Space Institute and the physics department. He's working with Vicky Caspi on the CHIME collaboration, and he's going to tell us all about fast radio bursts. So go ahead, Marcus.
Cool. Thanks, Carolina, for the introduction. And thanks, everybody, for tuning in online to this public lecture. I hope that I can teach you all a little something fun about astronomy during these trying times. So just to reiterate and give myself another quick introduction, I'm a second-year master's student studying at McGill University in the physics department, and I'm associated with the McGill Space Institute, which is the section of the physics department that deals mostly with astronomy. And I'm supervised by Professor Vicky Caspi, and I'm a part of the Canadian Hydrogen Intensity Mapping Experiment Fast Radio Burst Project. So that's pictured on this slide, the CHIME telescope. And the purpose of the project is to use this telescope to detect fast radio bursts. And those are the sources that hopefully you will learn a little bit more about today. So I hope that I can share all of the excitement that I've had learning about FRBs these past couple of years with you. So to jump right into the talk and give a quick overview about what I hope you'll all take away, these are the sort of questions that I hope you'll be able to answer by the end of the presentation. So first of all, I want to dive into how we detect radio emission. So how in the first place are we able to detect the emission that comes from radio sources on the sky? What is fast radio transient astronomy? So FRBs are one source in fast radio transient astronomy, but how did this field begin? What are fast radio bursts, which is the main part of this talk, and it's the type of source that I study. Why is detecting FRBs so difficult? It's been a really interesting problem to try to solve in the framework of observational radio astronomy. What are the major discoveries in the field, of which there have been many over the past 2 years, which I'm really excited to share? And finally, why should we care about FRBs at all? So to jump right into things, I'm going to give you a little introduction on radio waves. So this is a cartoon picture some of you might be familiar with. This is just a simple AM/FM radio that many of you have probably seen before. And there are a couple of features on it that I want to point out immediately. The first is the antenna on top. And this is what we call a dipole antenna. And it's the part of the radio that's actually used to detect the radio waves that come from either terrestrial sources or, in the case of radio astronomy, from astrophysical sources. I also want to point out the knobs on the bottom and these numbers on the bottom. And what these knobs do is they allow you to adjust what radio frequency you're tuning into. So you might adjust these to a particular AM radio station to listen to your favorite daytime broadcasting, or to an FM radio station to listen to some of your favorite tunes. So the way that radios work is that you can imagine that radio waves are just another wavelength of light. They're just like optical light, except their wavelength is different. So they have a much longer wavelength, which means that we can't see them with our eyes, but they're detectable still by electronics. And so what the dipole antenna on the radio does is that it has charged particles inside of it. And what the radio wave really is just a perturbation in the electromagnetic field that travels through the dipole antenna. And what this does is it causes the charged particles in the dipole antenna to oscillate around. And this oscillation can be detected as a current or a voltage in the electronics of the radio, and this can be converted to sound, which you can hear. So the major takeaway here is that antennas, dipole antennas, like the kind you see on this cartoon radio, can be used to listen to radio waves, and we can tune in to specific radio frequencies. So now we know a little bit about detecting radio emission with antennas, but how do astronomers manage to detect the faint, far-away radio emission that we do from astrophysical sources? So when we're detecting daytime radio waves, those come from radio towers on Earth, but we're detecting astrophysical sources. And how do we do that? So this is a picture of the Parkes Radio Telescope at the Australian Telescope National Facility. And this is the telescope that was used to detect the first fast radio burst in the early days of FRB astronomy. And what I first want to point out is the parabolic shape of the radio dish. This dish is 64 meters in diameter, which is huge. And that size is necessary because to make the incredible discoveries we do in radio astronomy, we need these enormous telescopes to collect all of this radio emission, as astrophysical radio emission tends to be very faint. So housed in the box above the center of the paraboloid is the receiver antenna. And I won't go into too much detail about these because they're quite complicated, but in essence, they're not too dissimilar in concept to the simple dipole antenna we talked about with the AM/FM radio. So the reason for the parabolic shape of many radio dishes is that this paraboloid allows parallel waves of light that are coming in from one direction on the sky to be focused to one point. And that point is where we put the receiver antenna. This focusing to one point allows radio dishes to have such high sensitivity. So we have a little bit of a picture about how radio dishes collect light, radio light from the sky, but what does that radio sky actually look like? So this is a little comparison picture of the sky in optical wavelengths, so what we see with our eyes on the left, and radio wavelengths, so what a radio telescope would see on the right. This left image shows the familiar Milky Way with the many stars and dust lanes. This image was probably captured with a decent amount of exposure time and a nice camera. While the right image shows many point-like radio sources in the sky, as well as some other curiously shaped perturbations. So something I want to point out is that these point-like sources are not actually stars. They're extremely distant radio galaxies. These radio galaxies contain supermassive black holes that we call active galactic nuclei. And in this active state, we sometimes call these active galactic nuclei, or AGN, quasars, which is a contraction for quasi-stellar radio source. And quasi-stellar just comes from the fact that, in this image, you can see they really do resemble sort of point-like stars in the distance of the radio sky. And these more broad perturbations on the sky come from turbulent locations in the Milky Way. In major star-forming regions, young massive stars explode relatively quickly at the end of their lives. And by relatively quickly, I mean like millions of years. But that's kind of fast compared to the 14 billion year age of the universe. So bear with me in terms of timescales. But these explosions, or supernova, leave behind remnants which produce faint radio emission and show up as these kind of perturbations on the radio sky. So this is a static picture of the radio sky, but what I study are fast transients. So what are these fast transients that I promised at the beginning of the talk? So this is a picture of the woman who first discovered pulsars. Her name is Jocelyn Bell Burnell, and she's basically every fast radio transient astronomer's hero. She's pretty awesome. So she's pictured here at the Mullard Radio Astronomy Observatory in Cambridge. And funnily enough, that radio telescope in the background, it's called the 1 Mile Telescope. It isn't actually the telescope she used to discover pulsars, which is what she's famous for. But she's pictured with it there anyways, and the telescope that she did use to discover them is also at the Mullard Radio Astronomy Observatory. So Jocelyn Bell Burnell discovered pulsars, which were sort of the first major fast radio transients that we started studying in radio astronomy. But what actually are pulsars? So pulsars are the dense stellar remnants that are left over after the supernova of a relatively massive star at the end of its life. So you can imagine taking a star that's maybe 5 to 8 times the mass of our sun and then squeezing it all into this super dense neutron-rich material that eventually shocks back into this giant supernova explosion. But what's still left behind at the end is this very, very dense stellar remnant made of almost entirely neutrons. So pulsars contain nearly the, maybe 1.5 to 2 times the mass of our sun in a diameter of about 20 kilometers. So you can imagine taking this sphere about the size of Montreal and putting the mass of the sun times 2 inside of it. And suddenly you have this super dense object that's off doing crazy things in our galaxy. And it's so dense that a teaspoon of this material would weigh as much as Mount Everest, which is just crazy to even think about. So one special thing about pulsars is that they have extremely strong magnetic fields. And these extremely strong magnetic fields mean that charged particles around the neutron star will spiral around these magnetic field lines. And it's this spiraling around the strong magnetic field lines that results in radio emission in these lighthouse-like beams that spin in and out of our line of sight that you see in this animation. So pulsars spin a lot faster than another astronomical object like the Earth. Their period of spin ranges from milliseconds to seconds, which is incredibly fast for something of its size. So these objects are very extreme. We can see these little blips of radio emission showing up in the bottom as the pulsar radio emission goes into and out of our line of sight. And this pulsation is super, super stable. So that means that you can take the period of a pulsar and you can expect that period to stay very, very constant over time. So unlike our watches that some of you might wear that eventually start drifting and not telling time properly anymore, pulsars don't do that. They are so extremely precise in their periods that they're some of the most precise clocks in the universe. Another fun fact about pulsars and pulsar emission is that they can also make beautiful graphics. So this is the album cover of Joy Division's Unknown Pleasures for any of you English rock fans out there. And this album cover actually comes from the thesis of a pulsar astronomy in the late 60s. So basically each of these lines represents one of the pulses of one of the first discovered pulsars, which is pretty cool. So how did Jocelyn Bell Burnell discover pulsars? Well, now on the slide is a picture of the paper, which was reading out radio signals from the array that she used to discover pulsar signals. And originally, her and her supervisor thought that these signals were just interference from some terrestrial source. But what Dr. Bell Burnell noticed, and that led her to believe this source was astrophysical, is that it showed up in the radio telescope 4 minutes earlier every day. And the reason why this implies an astrophysical source is because relative to the sun, the Earth completes one rotation every 24 hours. But relative to far away astrophysical sources, because the Earth is orbiting the sun, and that causes an extra 4 minutes in terms of its orbital rotation relative to the sun, that doesn't occur for these faraway astrophysical sources. So they actually appear on the sky 4 minutes earlier each day. And that's what Dr. Bell Burnell noticed, which allowed her to realize that this source was actually astrophysical, and that led to the discovery of the first pulsar. And this is now a still booming area of astrophysics that many people study, and we've learned so much from pulsars. So I've talked about pulsars, which was the first major fast radio transient, but now let's talk about fast radio bursts, which is the meat of this talk. So fast radio bursts emit emission that's like what we see from pulsars, but instead of periodic, it's sporadic. So we don't know when they're going to occur. They're randomly located on the sky. So we don't know where they're going to occur. And they're extragalactic. So pulsars are pretty much all in our galaxy, or the dwarf galaxies that are around the Milky Way that we've discovered, whereas fast radio bursts are bright enough to be seen from outside of our galaxy. And this animation is just showing you how fast radio bursts can be going off all across the sky at any time. And I put an asterisk next to sporadic because usually fast radio burst activity is sporadic, but in at least one source, we can actually well predict its activity, but we'll get to this later. So I've mentioned that FRBs are extragalactic, but how can we be so sure that it's not a signal coming from outside of, or inside of our galaxy, rather? So this is a plot from the very first FRB detection by Duncan Lorimer. His team used the Parkes telescope to discover the first FRB, FRB 010724, which is just the year, month, and day of the FRB discovery. And this burst is usually just referred to by the Lorimer burst. And I'm going to give a quick description of what you're seeing on this plot because it's a bit hard to interpret, but it's also really important to understand. So this image is what we call a waterfall plot. And on the x-axis is time, and on the y-axis is radio frequency. So you can imagine on the y-axis, if you go back to our picture of the radio, tuning the radio station up and down the different frequencies on this axis. And then the color scale in the center part of the image shows the radio intensity. So darker means brighter in radio intensity. That big sweep going across the image is the Lorimer burst itself. So the most important aspect of this plot is that the radio emission doesn't all occur at the same time. It's actually lower radio frequencies arrive later compared to those at higher radio frequencies. This is an effect we call dispersion, and it comes from a result of the radio emission traveling through diffuse plasma in and between the galaxy towards us. Note that the inset plot is dispersion corrected and then sums up all the frequencies, so you don't see any sort of sweep in that inset plot. So we know that FRBs come from outside of the galaxy because the amount of dispersion we see in them is a lot more than for galactic pulsars. And we also know that FRBs must be super bright because since the pulse is from much farther away, it comes from outside of the galaxy, but we can still detect it. That means it has to be way brighter than pulsar pulses. So this was the first discovery of an FRB, and we first found it in 2007. It was found by looking at archival data, which is why it was published in 2007, but the burst was labeled as found from 2001. But then years went by without finding any more signals like this. And this begged the question as to whether these signals were really astrophysical, or like Jocelyn Bell had been thinking to herself, did this maybe come from some kind of terrestrial source? So this begs the question of saying, is the signal interference or astrophysics? And this is a graphic that's just sort of showing a bunch of the different electronics and radio emission mechanisms that can screw up radio astronomy observations. Radio astronomers really don't like the fact that this happens. It makes it really difficult to do a lot of the amazing astronomy that we do, but we persist, and we were able to figure out and discern which of the signals we see are from terrestrial electronics and which are from astrophysical sources. But as you can see, there are many electronics which cause us difficulty in terms of discerning astrophysical signals, and even airplanes flying overhead, for example, can reflect radio emission from cell phones in large cities to be caught by radio telescopes. So it's a big problem to try and make this discernment. And this is maybe a more close to home example of how electronics can interfere with radio transmission. So this is an example of taking old over-the-air television signals and then seeing what the interference looks like from different electronics that might be turned off, or turned on rather. So you can see that in the top left is the normal image, and then the other panels show different electronics and the interference that causes in the over-the-air television image. So this isn't just a nuisance to astronomers, it's also a nuisance to anybody wanting to watch a good episode of TV. So while there was worry about these signals just being from interference, we were very happy to discover 4 more FRBs from the Parkes Radio Telescope in 2013. And while this meant that we had a sample size of greater than one event now, there was still a little bit of worry. And this was because all of the sources that we had detected so far came from the Parkes radio telescope itself. So one could say maybe these aren't actually still astrophysical signals, maybe they are interference, and that source of interference comes at the site of the Parkes telescope, which is why these kind of signals aren't being detected by other radio telescopes. This actually leads to a pretty funny story. So while Parkes was detecting astrophysical FRBs, and don't get me wrong, the signals that we see here we're pretty confident are astrophysical, there were also a number of signals that looked a lot like FRBs, but with slightly different properties, and which consistently showed up around lunchtime. So these signals, the researchers at Parkes affectionately called peritons, and a paper eventually was published as to the nature of the periton signals. And well, I'll just let everybody read the abstract of this 2015 paper by Emily Petrov quickly. And nope, your eyes are not deceiving you. Indeed, there was a paper published talking about how periton signals came from microwave ovens at the Parkes Radio Astronomy Observatory. And basically what happened is that there was a microwave oven on site, and at lunchtime people would go to heat up their food, and then they would open the microwave before it finished cooking in time. And if this microwave door opened prematurely and the telescope was at an appropriate angle observing in the sky, this emission could be picked up by the telescope, and it looked a lot like an FRB. But luckily, now we know that FRBs are not microwave ovens, which is extremely reassuring for everybody in the field. Okay, so we've determined that FRBs aren't microwaves, but that doesn't tell us what they are. So there's a huge number of plausible models for what causes FRB emission. And in fact, it was only within the past year or so that the number of detected FRBs exceeded the number of FRB models. So theorists were coming up with models faster than we could even detect the sources. To this day, there's still a lot more work to be done in narrowing down what astrophysical process really produces FRBs. But of the popular models, I'd say they can be grouped into three broad categories, which I'm showing here. So first, I'm going to talk about the model of FRBs, which comes from a cataclysmic origin, which here basically means that the production mechanism of the FRB destroys whatever the progenitor of the event was. So earlier I talked about supernova explosions. That could be one potential progenitor. But here on the right, I show an artist's impression of an event some of you might have heard of, known as gravitational wave 170817, which was the first ever detected neutron star merger. And many scientists have wondered whether neutron star mergers like this could produce FRB signals, since the supernova resulting from the merger is extraordinarily powerful. And the sort of smoking gun for this would be the association of an FRB temporally and spatially with a gravitational wave that looked like a neutron star merger. And we haven't made a detection like this yet, but such a detection would be extremely exciting and is something that we hope to be able to probe well in the future. So the next major set of models come from where FRBs are produced by some kind of super bright pulse from a pulsar. This usually ends up invoking a special kind of pulsar known as a magnetar. And magnetar basically just means pulsar, but with extremely strong magnetic field. So there are processes in the birth of the pulsar that lead to a stronger than normal magnetic field. So one way of producing super powerful pulses from a pulsar or magnetar is sort of shown in this artist's impression on the right. So I've written down giant pulses, and maybe these extremely energetic pulses could come from a deformation on the neutron star surface, which might release a huge amount of charged particles. And if all of these charged particles were spiraling around the super strong magnetic field lines of a young magnetar, then they would emit crazy amounts of energy in the radio. And maybe that's what causes FRBs. There's also suggestions that neutron stars could drive shocks in the surrounding medium to cause FRBs, or that stray asteroids around a pulsar or a magnetar could impact the surface and lead to an FRB event. So finally, the last set of models that I want to talk about are the exotic origin models. And basically, these models involve super exotic interactions, which are very hard to explain, and I am absolutely not an expert in, which is why I put a bunch of question marks here. But usually the explanation of these models involves a lot of heavily technical jargon, talking about things like cosmic strings, dark matter, axions, neutrinos. So I won't go into too much detail about these kinds of models, but needless to say, these are some of the hardest FRB models to prove because their origin is so exotic, but they're still definitely a possibility and worthwhile to consider. So one important point I should make is in regards to cataclysmic models. And what's interesting about cataclysmic models is that in principle, if you're destroying the source of the fast radio burst when it goes off, then it shouldn't emit more than once from the same sky location. So this brings us to one of the biggest discoveries in FRB astronomy, which was the detection of the first repeating fast radio burst, FRB 121102. And this FRB was incredibly exciting for the field, and it's taught us so much about fast radio bursts. And there's just a ton of reasons why this source has been so incredible for fast radio burst astronomers. So the first reason why it's been so amazing is that it was the first source not detected at Parkes. It was detected by the Arecibo telescope in Puerto Rico, which is this huge 300-meter dish that's pictured on the right. And this really helped us believe, again, that fast radio bursts aren't from terrestrial interference, but are, in fact, astrophysical sources. So then what made 121102 so extraordinary to fast radio burst astronomers is that it was the first source found to repeat. Arecibo did some follow-up observations of this source, and in 2016, it found another burst, which is completely unprecedented. It was a super exciting moment for the field, and it really changed how we think about fast radio bursts. So a really cool thing about this repetition is that since we knew that the source could go off more than once, it means that we could observe it with other radio telescopes and be confident that eventually we could detect something from that sky location. So basically what happened is radio astronomers decided to look at this burst with arrays of telescopes, which are really good at pinpointing radio emission to very specific locations on the sky. And in particular, they looked at FRB 121102 with the very large array, and they found a burst. And this burst allowed them to localize the source of emission to a very small location on the sky. And then optical follow-up observations with the Gemini telescope allowed us to find the host galaxy of FRB 121102, which is huge because we'd never found a host galaxy for fast radio burst emission before. So the host galaxy of FRB 121102 is pictured on the right. And weirdly enough, the galaxy that we found the burst to live in is a dwarf galaxy. And the reason why this is so surprising is that dwarf galaxies contain a really small fraction of all the stars in the universe. So if you would expect stars to be somehow the source of fast radio bursts by something like a supernova or exploding into a young pulsar or magnetar to give off these giant pulses, it's odd that this repeating burst would be found in this, low stellar mass dwarf galaxy. So finally, the kind of last reason why FRB 121102 is so particularly awesome is because follow-up observations in extremely fine scale radio by the very long baseline interferometry set of telescopes, we found that there was persistent radio emission co-located with FRB 121102. So not only was it producing this bursting emission that we saw repeat from the same location on the sky, there was also this persistent source that emitted more faintly but persistently at the same location as the fast radio burst. So this has led to much speculation about the persistent radio emission potentially being from something like a surrounding supernova remnant. So while FRB 121102 gave the FRB community tons of excitement and awesome discoveries from 2014 to 2018, we've really just begun to move on to a new era of FRB science. And so I'm going to talk to you about two surveys, which are really kind of just changing the game of fast radio burst astronomy right now. The first of these is on the left, and it's the Australian Square Kilometre Array Pathfinder, or ASCAP, which uses its survey called the Commensal Real-Time ASCAP Fast Transient Survey, or CRAFT. And that CRAFT survey has done a very good job at localizing FRBs, which I'll talk about more soon. And pictured on the right is the Canadian Hydrogen Intensity Mapping Experiment, which I mentioned at the beginning of the talk, or CHIME. And this is the collaboration that I'm involved in, and it's super exciting. So as you can see, the CHIME telescope doesn't quite look as traditionally parabolic in shape as the ASCAP dishes, which for the purposes of FRB science actually ends up working to its advantage. And I'll get to that in just a bit. So zooming in on ASCAP, this survey uses a set of 36 parabolic dishes and interferometry techniques to search for and localize fast radio bursts to small regions on the sky. So interferometry is basically the technique of coherently combining the signals that you get from multiple radio dishes and using this combined signal to pinpoint exactly where on the sky the radio emission comes from. So the same technique that was used to identify exactly where on the sky FRB 121102 came from with the very large array, but this is happening in real time and covers a larger sky area. So ASCAP finds a moderate amount of FRBs. It's more than a lot of other previous FRB surveys, but it's still not as many as a survey like CHIME. In about 2 years of surveying, they've published about 30 fast radio burst sources. But ASCAP's main strength isn't finding a crazy amount of FRBs. It's, like I've said, localizing those sources of radio emission to very small regions on the sky. And with this, if the region on the sky is sufficiently small enough, we can discern what the host galaxy of the radio burst must have been. So moving on to CHIME, the CHIME telescope uses a set of 1,024 antennae across 4 cylinders, so 256 antennae per cylinder, and these cylindrical dishes to find a huge number of FRBs. The use of cylinders instead of fully paraboloidal dishes means that CHIME's sensitivity on the sky covers a really large amount of area, much more than any survey that came before it. So if you remember earlier when I was talking about the parabolic shape of radio dishes, that pinpoints it to a very specific sky location, but opening up that one axis to this cylindrical shape really allows CHIME to see a whole huge swath of the sky. So because of that, CHIME is amazing at finding more FRBs than any other FRB survey. And in particular, CHIME doesn't actually have any moving parts. So you don't point CHIME at some direction on the sky. You just let the sky do the job. The Earth's rotation, as it rotates, the sky will scan itself overhead, and different parts of the sky will come into view of the telescope. And so since CHIME just sits there and stares at what's passing over above it, we look at the same regions of the sky daily. And what this means is that CHIME is particularly good at finding repeating sources, since it's scanning those same regions of the sky day to day. And if a burst were to go off twice, we have a much better probability of seeing it, since we're going to be seeing that same location on the sky so often. So to round off this talk, I'll quickly go through some of the major recent discoveries made in the past year and a half with CHIME and ASCAP. So first, I'm going to talk about CHIME's discoveries. And at the very beginning of 2019, CHIME FRB made the cover of Nature with its first results. And this is huge, since publishing in Nature is pretty much every scientist's dream. And CHIME FRB not only published in Nature, but made the cover of the magazine, which we're all super proud of. So the first results from CHIME included the discovery of 13 FRBs, but in particular, what made this first set of 13 FRBs so special was that one of the FRBs was another repeating source. So for a long time, FRB 121102 was the only FRB we knew to repeat, but within months of turning on, CHIME actually managed to find another repeater, which really showed us that 121102 wasn't just a really special source. There are more repeating FRBs out there. So since CHIME's first 13 FRBs and the new repeater, we've discovered 17 published new repeating sources on top of that since, which is huge. Years ago, fast radio burst astronomers could barely even fathom the discovery of one repeating source, let alone 17 new ones in the span of a year. So this is super exciting because it means that CHIME FRB might be able to start statistically answering the question as to whether or not all FRBs are repeating sources. And some of those sources we just haven't been able to see repeat yet. So you can imagine that if all FRBs repeat, eventually we might detect repeated bursts from all of them. This is something that is really difficult to answer, but with CHIME's results, we might be able to come to a statistical conclusion sometime in the future. So shaking up the field yet again, one of the really exciting discoveries that CHIME has made is that one of these 17 new repeating sources actually repeats periodically, which is crazy. So it repeats periodically every 16.35 days, approximately, which means that about every 16 days, we expect to start detecting that particular source again with the CHIME telescope. Earlier in the talk, I mentioned that there's one source which we know doesn't go off sporadically. We can predict its activity. Yeah, this is the source that I'm talking about. And what's more is that not only is this source periodic, because it's periodic, we've been able to do follow-up observations with those interferometers I talked about to localize it to a host galaxy. And so pictured on the right is the host galaxy of this periodic repeater. And it's a nice spiral galaxy, so quite a bit different from the host galaxy of FRB 121102. And that little green circle is the localized region that we know the source is contained within. And it's actually a star-forming knot in this spiral galaxy, which means that the source is in a region of high star formation, which has implications about what exactly the source might be. So the fact that this repeater repeats periodically poses a really interesting question for theorists who are trying to come up with models for FRB emission. And at least for this source in particular, theorists have to come up with a way to explain the periodicity that we see in this burst. And so finally, and most recently, arguably most incredibly as well, CHIME FRB has detected an extremely strong radio burst from a galactic magnetar. So this discovery we just made months ago. And the reason why it's so exciting is because this is the first time that we've ever been able to associate a fast radio burst with an actual source. So we've only been able to hypothesize about what the source of fast radio burst emission could be for all of these extragalactic sources. But because we've detected before this galactic magnetar, and we saw a super energetic radio burst come from the magnetar, then we know that that magnetar must have been the source of the radio emission. So, what's interesting to note about this burst from the magnetar is that it was extremely bright, but since the magnetar is in our galaxy, we expect things to be detected much more easily and much more brightly because they're far closer than things that are extragalactic. So even though this lit up our telescope like crazy and we saw its super energetic emission, in reality, when accounting for the distance of the source, it's actually still an order of magnitude or so weaker than the emission we see from most extragalactic fast radio bursts. So it shows that magnetars have the possibility of producing emission energetic enough to be FRBs, but we'll have to wait and see if any other magnetars produce emission like this to be more certain. in the future. So it seems kind of absurd to say, but truly each of the discoveries on this slide has completely changed the game of FRB astronomy, and they've all happened within the span of a year and a half. So needless to say, it's a great time to be an FRB astronomer. So to round off the discussion on the importance of FRBs, I just wanted to talk about this really recent result from ASCAP. And so remember earlier how I said that fast radio bursts are dispersed across radio frequency because of the plasma that exists in and between galaxies in the universe? So this actually makes fast radio bursts an exquisite probe of the matter that exists along the line of sight. And you can see that in this graphic where if you had completely empty space, all of these different frequencies of emission represented by the different colors would arrive at the same time. But because of this effect of dispersion, which we can measure exquisitely with fast radio bursts, we can account for the matter that occurs along the path of fast radio burst emission. So the reason why this is so important is because there's been this huge problem in cosmology for a long time that, based on our current understanding of the universe, we haven't actually been able to account for all the matter we expect from theory with our observations. So this means that when we take all of the stars and dark matter that we find in galaxies and add it all up, it doesn't quite match with how much matter we expect there to be based on theoretical means. So what we've been able to do with fast radio bursts, and recently ASCAP localized 4 fast radio bursts, or rather 5 fast radio bursts sufficiently well to host galaxies in order to probe the missing matter that exists in the universe. And they showed that by accounting for the matter that you're able to probe with fast radio bursts, you can indeed make up the difference between what we've observed so far of matter in the universe and what is expected from theory. So we'll be able to do an even better job statistically of this in the future with more FRB localizations, but ASCAP's already managed to do quite a good job. So just to conclude on where the status of fast radio burst astronomy is right now. So FRB astronomy is one of the hottest and fastest growing fields in astrophysics. It's super exciting. I'm super proud to be a part of it. And as you can tell from the past couple of slides, we're making huge strides in such a short period of time. And surveys like CHIME FRB and the ASCAP Craft Survey are seriously changing the game. And there's even more upcoming surveys that are going to join CHIME and ASCAP to do an even better job at detecting fast radio bursts. So expect more incredible discoveries from CHIME to come, including a population of hundreds of FRBs that we're working hard to analyze for publication right now, and a lot more in general from fast radio burst astronomy in the future. So thanks everybody for listening in, and I'll hand things off to Carolina to ask some questions from everybody.
Oh, so thank you so much, Marcus. That was awesome. We have some questions from the audience already. If you have any more, just feel free to put them in the chat or in the comments on Facebook. So we'll start off with, do we think that all FRBs have the same type of source, or that they might have different kinds of sources?
That's actually a really great question. And that sort of also ties in with the discussion on whether we think all fast radio bursts are actually repeaters or not. So it's definitely possible that there could be multiple sources which are causing fast radio burst emission. So in particular, for example, if you were to posit that all fast radio bursts had to come from neutron star mergers, we've actually shown that that statement is probably wrong, because the rate of gravitational waves we detect from neutron star mergers is much smaller than the rate of FRBs in the universe. So it's definitely possible that there are multiple sources of FRB emission, and in particular, it's possible that there are cataclysmic sources of FRB emission, which cause only one-off FRBs, and that there are a set of repeating sources of FRB emission, since so far we can broadly categorize FRBs into those two classes.
On a related note, could we discriminate between galactic and extragalactic FRBs from their signal structure?
Ooh, from their signal structure. So the only galactic FRB we've detected was that one event from the magnetar I mentioned earlier. And then every other fast radio burst we've detected is extragalactic, just based on the amount of dispersion we've seen in it. In terms of fast radio burst signal structure, so if I go back to these are waterfall plots for a bunch of the new repeaters that CHIME has discovered. And so this is the radio frequency and time, where the color on the plot, as we remember, shows the strength of the radio emission. And what's interesting about these repeating sources in particular is that repeating FRBs tend to show really complex structure in this frequency time plane. So, in terms of discerning between galactic and extragalactic events, we only have one galactic event so far. And we normally discern between those by being able to associate emission with a galactic source and comparing the amount of dispersion to tell us whether the source is within or outside our galaxy. But what's interesting to note about structure is that in terms of repeating and potentially non-repeating FRBs, the ones that we've seen to repeat tend to show complex time structure, frequency time structure in these waterfall plots. So it's definitely an interesting thing to consider when you see an FRB go off. If it has complex frequency time structure, you might expect it to repeat sometime in the future, although this correlation has yet to be, fully proven.
Okay. We have a question about pulsars that came in early. So is the reason for the preciseness of pulsar periods known?
That's actually a really good question. I'll try to think of something quickly. So is the reason for the preciseness of pulsar periods known? So just thinking this out, what causes pulsars to spin so quickly is that, all stars have some sort of degree of rotation to them. So our own sun is actually rotating. It's just that you can't really tell when you look at it with your eyes. Don't look at the sun with your eyes. But even if you look at it through a telescope, it's rotating very slowly. But when a star undergoes supernova at the end of its life, if it's massive enough, through the conservation of angular momentum, since you're taking this really big object and compressing it into a much smaller amount of space, it starts spinning a lot faster. And so from conservation of angular momentum, pulsars spin really quickly. And I guess for them to stop spinning so quickly, or to slow down their period of rotation, they need to have some sort of angular momentum loss. And I guess that, whatever processes cause angular momentum loss in pulsars are not strong enough to cause them to lose the preciseness of their periodicity very quickly.
Okay. Now to change a little bit, we have a few questions about instrumentation and the instruments that we were using to detect FRBs. So how can a CHIME detection be localized by another radio telescope, like the Parkes telescope, for example?
So CHIME detections on their own can only be localized to a fairly broad region on the sky. Let me just see if I can get to a picture of CHIME. Right. So, ASCAP is the set of parabolic dishes that's really good at localizing FRBs in real time to a precise location on the sky. But CHIME, just because of the way it's designed and the instrumentation, isn't quite as good at doing that. So when we detect an FRB with CHIME, if it's only gone off once, we usually can't localize it to a host galaxy because the region on the sky we can say the FRB lives in is too big. But in the case of a repeating FRB, you could do follow-up with other telescopes, and you could use interferometry with other telescopes to look at the repeater and localize it to a host galaxy. So that's what we did with this source, the periodic repeater. We looked with a telescope that wasn't CHIME, so the VLBI array, and we were able to localize that source. So follow-up of repeaters is a great way to do localization. In the future, we hope to build other telescopes around the world that we could use in concert with CHIME, looking at the same region on the sky, to try and do localizations in real time. But that's a problem for the future, and it's a bit far off for now.
Well, there are two related questions that have come in to that. So one of them is whether CHIME has made progress on setting up a remote site for interferometry, and if the instruments we have are at our disposal are enough to conclude on the origins of FRBs, or what would we need in order to do so?
So I'm actually not sure how much I'm allowed to talk about the progress of interferometry with CHIME, but needless to say that work is underway to do interferometry with more CHIME-like instruments at different sites. And in terms of whether the instrumentation we have right now is good enough to conclude on the nature of FRBs, I would say no. I think really what we need is many FRB localizations. So right now we only have 9 FRBs localized to host galaxies, I believe. But with many more FRB localizations, we might be able to make a connection between the type of galaxies that FRBs live in and the type of progenitors that we might expect to exist within those galaxies. So I'd say a conclusive, understanding of the nature of FRBs is a bit of a ways off. But also a lot of people are super excited at the idea of magnetars as FRB sources, since we saw a super bright radio burst from a galactic magnetar. So, some people are really eager to say all FRBs are magnetars now, but I don't think it's that conclusive yet.
We have time for a couple more questions. I have one more, but if anyone has any others, you can add them. So is the frequency sweep of FRBs always in the gigahertz range?
Right, so that's a great question, actually. Very observant. So in this plot, we can see that the frequencies of the radio emission are from 1.5 to 1.2 gigahertz. That's just a result of the instrumentation of the telescope that was used to detect this burst in particular. So this is a receiver that looks at those frequency ranges. It's a very common frequency range for radio astronomy. I'm not actually sure why, but I do know there are a set of radio frequency bands that are supposed to be sort of sectored off for radio astronomers to use so that the radio frequency isn't super polluted. Maybe it exists within that range. But anyways, there are receivers which actually look in other frequency ranges. And in fact, CHIME itself doesn't look in the gigahertz frequency range. It actually looks in the megahertz frequency range. So if we go to these waterfall plots, I don't have the y-axis labels on the emission here, but this is actually from 400 to 800 megahertz. So the Parkes detection was from 1.2 to 1.5 gigahertz, and the CHIME detection is from 400 to 800 megahertz.
Okay. We have one question that just came in. So someone says that they saw on Instagram that CHIME announced the first detection of FRB that repeats with predictable frequency. How do we discover that FRBs have predictable frequencies? And what does the news mean? Maybe that's the better question.
Right. So that's probably talking about this discovery right here. And basically what that means is that since the sky is just sort of passing over the CHIME telescope every day, there's a certain location on the sky where a repeating FRB lives. So you can take that location on the sky, say you were tracking a star, you could just point at that star and follow it as it passes over the sky. You could do the same thing with a repeating FRB, it's just you don't know where that FRB is with your eyes. But in principle, somewhere far away, that FRB exists at that location on the sky. And so since this location on the sky is passing over CHIME every day, we're exposed to it and we're sensitive to radio emission from that region. And so what happens is that this repeating FRB is, giving off radio emission. And, it's maybe not always giving off radio emission when it's overhead of CHIME, but it's giving off radio emission nonetheless. But when it is over CHIME, if that radio emission is strong enough, we can detect it. And so what happens is that we've detected this source from that location on the sky, and then we've seen it occur again in the CHIME telescope every 16 days. So it's basically just a result of waiting and seeing that the same source pops up every 16 days that has allowed us to determine its periodicity.
Good. So it's almost 8 o'clock. So thank you so much, Marcus, for the talk. It was awesome. And thanks everyone for your questions. We will be having another one of these public lectures next week. The exact date will be announced on Facebook soon. And the topic will be why and how physicists can contribute to non-physics fields with a focus on machine learning and biology. So we hope you'll join us for that. And thanks again for joining us for this. Have a great night, everyone. And thanks again, Marcus.
Yeah, thanks everybody for tuning in. And thank you, Carolina.